Great question. It's kind of obvious to say it's possible into the future, because of course that's what we're doing, we're moving into the future. It then gets interesting because you say, well, why do we have to go into the future? Why can't I stop going into the future? Well, you can vary the rate at which you go into the future relative to someone else. For example, if I was to get in a rocket now and accelerate off, even at 1g, right, just a sort of acceleration I could take, and head off and end up traveling relatively close to the speed of light, and let's say go to the Andromeda galaxy, and then, which is 2 million light years away from the perspective of the Earth, and then turn around and come back again. If I go close enough to the speed of light, I could arrange it so I would age, let's say, a year on the outward journey and a year on the inward journey, and you could do that calculation. But 4 million years would have passed on Earth. So I would come back on that journey 2 years older, but I'd arrive at the Earth 4 million years in the future. So that's special relativity. That's Einstein's theory published in 1905, not even the theory of gravity. So time travel is possible into the future, and it's inevitable that you travel into the future, and you can vary the rate you go into the future relative to someone else by the way that you travel around. In the past, Einstein's special theory of relativity from E equals mc squared, that thing in 1905, says no, you can't, because of the geometry of space and time themselves. His general theory of relativity, where space and time can be curved, that's his theory of gravity. The correct thing to say is that we can imagine distortion, geometries is the best way to say it. We can imagine geometries of space and time. Wormholes would be an example, where if you could go through them, you could travel into the past. However, we don't understand enough. So you can calculate these things, but whether or not they're possible to make is an open question. Most people think not. And the last thing I'll say, Stephen Hawking wrote a very famous paper called the chronology protection conjecture. And conjecture is important. So he conjectured that whatever the ultimate laws of quantum gravity are, they will be such that you can't build time machines that you can use to travel into the past. Well, Mandy and Matthew, I think the answer is no. So I've finally been able to give a definite answer. The reason for that is that if you look at Einstein's theory, both his theories of relativity, which are our best description of space and time, then the speed of light plays a very specific and important role in those theories. And what it does is it enforces what a physicist would call causality. So it's kind of a big word. What does that mean? Well, it's actually meaning that cause and effect are always respected. So if I throw a ball of paint, let's say, at that wall over there, and it smashes into the wall and all the paint smears over the wall, then you would think, well, it'd be a funny kind of universe if I could arrange things so I would see all the paint appear on the wall before I threw the paintball at the wall. Indeed, it would. It doesn't seem like a universe that would be logically possible. But if you can travel faster than the speed of light in Einstein's theory, then that's what can happen. You can reverse cause and effect. So the speed of light, so actually I should say it's kind of a bit of a red herring, because people often ask me, well, why? What's special about light? The answer is, there's nothing particularly special about light. In Einstein's theory, it's not really the speed of light, it's the speed of things that have no mass. So if you have no mass in Einstein's theory, you travel through space and time at the speed of light. And if you have mass, you travel slower than the speed of light. And light happens to be massless. So the photons, the particles of light that are streaming around in the room now, those things are massless particles. Why are they massless? Well, we actually know the answer to that now from the Large Hadron Collider. It's because they don't interact with something called Higgs bosons. So we even know the answer to that. But that's the thing. So basically, if you could travel faster than the speed of light, you could do silly things like reverse cause and effect. You could time travel into the past. You could do all sorts of nasty things like prevent your parents ever meeting and therefore seemingly preventing your own birth, which would be a paradox. So it's very important. It's built into the fabric of result in Einstein's theory of special relativity that he wrote down in 1905, the one from which E equals mc squared emerges, his most famous equation, is that moving clocks run slow. So quite specifically. If you're sat there in your room now where you're listening to this broadcast, or imagine us sat here, and imagine a clock flying past us, then that clock would run slow relative to us. It's not just we'd see it run slow, it would run slow relative to us. So that means that if I were to fly off now, let's say I flew off to Alpha Centauri, the closest star, or the Andromeda Galaxy, over 2 million light years away, and I flew off very close to the speed of light, and I came back again, then you would have aged far more than I would. In fact, thousands of years could have passed on Earth in the time that it took me to do my little journey. So time is, it's a famous saying, time is relative, but it genuinely is. Moving clocks run slow. That allowed you to get into the future. So you're allowed to time travel into the future by moving fast relative to somebody else. You get into their future. But as I mentioned before, the doors to the past, as far as Einstein's theory is concerned, are absolutely closed. And I think most physicists think that whatever theory replaces Einstein's theory, remember I said that we needed a new one to describe what happens in a black hole, for example. I think most physicists suspect whatever replaces it will respect that idea that time travel into the past is impossible, because it just doesn't seem to be a way to build a universe, to be able to have all those paradoxes that can occur. But travel into the future, you can do that. And I suggest actually, if you're, how old is everyone here? Are you doing it? 14, 15, 16?
A range of ages, yeah.
If you're, if you've done some Pythagoras, actually, so if you've done enough maths to do Pythagoras, you can go, there's plenty of books around actually that will explain how it is that moving clocks run slow in Einstein's theory. You only need Pythagoras to do that. So I suggest that you could go and have a look actually. If you're comfortable with a little bit of maths, you can go and work it out. I'll give you one specific example just to finish, because I have the number in my head, I know it. So at the Large Hadron Collider at CERN in Geneva, it's 27 kilometers in circumference, and we accelerate protons around that ring to 99.999999% the speed of light, very close to the speed of light. And at that speed, time passes 7,000 times more slowly for the protons than it does for the experimenters on the ground. So that's a 7,000 times time shift into the future, if you like, if you go that close to the speed of light.
Wow.
Oh, it's a great question, that. I should say what they are. So they're a bit like black holes, actually. They're a place where space and time, the fabric of the universe, is very curved. And what the picture is not just like a black hole where it's curved and it goes down to this singularity, whatever this is. And by down, you know what I mean, kind of, because you have to imagine 4 dimensions, and we don't want to do that. But anyway, wormholes would be, you'd picture them as, instead of sort of stopping at the singularity, they'd come and open out again to another bit of the fabric of the universe. So the analogy would be, so I came to Australia last week on a plane from London. And I had to fly all the way around, obviously, around the surface of the Earth, which took about 20 hours. But you could imagine taking a shortcut, drilling a hole from London to Australia, and then I could get here quicker, because that's a shorter distance than having to go all the way around. And wormholes work like that. It's one of the big questions in theoretical physics, whether those things, first of all, can exist. They can, given Einstein's theory. People can imagine that kind of geometry, if you like. But there's a question about whether they would be stable. So there's a question about whether, if you tried to send information through them, then they would collapse. And it's a big debate at the moment, actually. Stephen Hawking produced a paper, which has actually got a fancy name called the chronology protection conjecture. Now that means, in fancy words, what your question is, like, could you use it as a time machine to go into the past? And I think most physicists think not. They think that whilst they could exist, they would be unstable and collapse again. And so you'd never be able to send information through, let alone a person. Even one little light signal wouldn't get through it into the past. But we need, as we said before, the more advanced theory, the quantum theory of gravity, to be sure. So there is still a bit of a debate. But I think it's fair to say, I don't know if you'd agree, I think it's fair to say that most theoretical physicists think, well, although we can't prove it yet, we think that they won't exist.
It just gets messy I suspect it would.
People think about little ones, though, subatomic-sized wormholes that really might exist and really might be the key to understanding the laws of physics in a better way than we do at the moment. So it could be that on a subatomic scale, space and time are covered in these little wormholey things that go around, and that might have something to do with the world that we see today. But on the big ones, actually, you know.
In general relativity, so Einstein's, I should say what it is, Einstein's theory of general relativity is our best theory of space and time. And so it really is, as we talked about before, it's you imagine space and time as a sheet, just imagine it as a thing, sort of literally a sheet, a surface. And all the theory says is that if you put matter and or energy into that, then it curves it and distorts it, and it can stretch it and make it shrink. And so it's the response of space and time to matter and energy. So the simplest version would be the sun. So you put a big spherical ball of stuff in there, and it warps space and time such that the nice straight lines, something just travelling, minding its own business through that warped space. Okay. So light bends around the sun because it's just travelling through the curved space. The Earth goes round the sun because it's just rolling, minding its own business through the curved space. So an example would be, you might say, well, how does curved space, can that give rise to something that looks like a force, which is gravity? So the best analogy I know of is to think of walking around on the surface of the Earth. So if you stand on the equator of the Earth, and you with your friend, and you say, we're going to walk due north. So we're going to set off, let's say we're 1,000 miles apart on the equator, and we're going to walk due north. What's going to happen? So you walk in straight lines, you don't change direction, you don't do any accelerating, but the straight lines are the lines of longitude on the surface of the Earth. So as you go further and further north, you get closer and closer together. And if you carry on to the pole, you bump into each other. But nothing's happened. Right? There's no forces acting, it's just that you're moving on a curved surface. And so you get closer. And that's basically Einstein's theory of general relativity. So all you have to do to those folded kind of geometries is you have to try and specify where you would put the matter and what kind of stuff you'd put there to make the geometry fold in that way. And you can do it. So you can write down that geometry. So it's called a warp drive geometry, I think it's called. It's in textbooks. So you can do that to have a warp drive. The question becomes, what sort of stuff would you have to actually put into the real universe to make it warp in that way? And it usually turns out that it's the kind of stuff that doesn't exist, right? But it has properties. It's sort of matter or sort of energy that has properties that do not exist in nature as far as we can tell. But you can still write the geometry down. So the geometry exists. So you can do it, and you can do the calculations, and you can see the warp drive. You can construct wormholes that connect distant regions of the universe, which you could use as time machines. You can do all that in the theory, but in nature, you'd have to have the right stuff to do it. It tends to be weird stuff, like stuff that has a negative pressure or something like that. So stuff that has physical properties that are just bizarre, and that no matter or energy that we know of in the universe has. So that to make the geometry happen. Einstein was a genius because he thought very simply, often in pictures, about how the world works. And what fascinated him back in the early 20th century, so in 1905 or so, was a result from a Scottish physicist called James Clerk Maxwell, who predicted, although he didn't know it really at the time, but he predicted that light travels at the same speed no matter how you look at it. So it's a bit of an odd thing to predict that. Essentially, what I'm saying is if I fly to that spotlight now at the speed of light, or let's say 75% the speed of light, and go flying towards that light, the light will hit me in the face at the speed of light. Not twice the speed of light, or 1.75 times the speed of light, but the speed of light. It's very odd thing to predict. But that came out of the theoretical physics of the 19th century from experiments on electricity and magnetism. Einstein was the first person to take that genuinely seriously and say, what does it imply? What happens if I say nature does work like that? So no matter how I move relative to you, we all agree on the speed of light. Well, he came up with a beautiful so-called thought experiment to work that out, and I can tell you that in about a minute, and it's the heart of relativity. He thought of this thing called a light clock. So imagine that I've got a very strange kind of clock, which is just two mirrors sat there like that. And my pendulum is light bouncing between the mirrors. So we can imagine 1 tick, 2 ticks, 1 second, 2 seconds, 3 seconds. It works as a very accurate clock. But remember that we've agreed that we all agree on what the speed of light is, no matter how anyone moves around. So what happens if I get this clock, literally on this stage, and I just walk along the stage? What do you see? Right? You see the clock ticking, but because I'm moving, you see something that looks more like that, because I started off over there and I walked over here, so the light, from your perspective, bounced along like that in a triangle. What does that imply? Well, if it's really true that we both agree on the speed of light, we both think it's the same, then you see my clock run slower than I do. Why? Because the light had to travel further to make 1 tick than it did when it was standing still. So that's a prediction. It's a very strange prediction. It says that moving clocks run slow. Time slows down when you move.
Of them theoretically came very shortly after Einstein's theory of gravity was published in 1915, although it wasn't recognized as such at the time, this glimpse. But essentially, what does Einstein's theory do? It's important for what follows. It's a theory of space and time, and how space-time, which is often described as the fabric of the universe, responds, warps or curves, to matter and energy in the universe. So the equations, basically the theory that Einstein published all those years ago, will say, give me some distribution of matter, something like a ball of matter, and the equations will tell you how the fabric of the universe is distorted. And by the way, the force of gravity in that theory then is the response of everything else in the universe to that distortion. So Einstein would say, what are we feeling now? Newton would say it's a force between us and the Earth, right? But Einstein would say there isn't a force. What we're responding to the distortion in the fabric of the universe created by the Earth. So that's John Wheeler, actually, the great physicist, put it beautifully. He said, matter tells space-time how to curve, and space-time tells matter how to move. And that's it, right? So that's Einstein's theory. So in 1916, shortly after it was published, a man called Karl Schwarzschild remarkably managed to solve the equations for a perfectly spherical, non-spinning ball of matter. It's the simplest thing you could do, which tells you how space and time are distorted by it. And that's a model for a star. It's the simplest thing you could do. So he solved the equations. It's a remarkable thing. In those equations, there is a description of a black hole, although it wasn't realized at the time. It's a remarkable piece, simple piece of mathematics, actually. So essentially, what's the idea behind a black hole? One way to think about it is that could you remove the star from this fabric, but leave the distortion behind? So if you do that, you get the description of a black hole. But you might say, what do you mean? How can that be formed in nature? So you think about what a star is. Then a star is a balancing act. So it's a mainly hydrogen and helium collapsing under its own gravity. That's how our sun formed 4.5 billion years ago. So it's collapsing. So what stops it collapsing? Well, as it collapses, the core heats up, and that initiates nuclear fusion reactions in the core. In the case of our sun, it's hydrogen being fused into helium. That releases energy, which creates a pressure which holds the thing up. So it's balancing, but it needs the fuel. And it's not infinitely big, of course, so at some point it runs out of nuclear fuel, and ultimately no more fusion reactions can occur in any star. And so the star will resume its collapse. So the question is, well, is there something that stops it? Because if there isn't something that stops the collapse, then it will collapse without limit.
And so actually, if you look at the history of physics in the 20s and 30s, people were saying, well, we'd like to avoid this idea that the thing will collapse without limit, because if it does, then Schwarzschild's equation predicts some very strange things indeed. And so people kind of tried to avoid it. It was really actually Oppenheimer and his student Schneider in the late 30s, just before the Second World War, that showed that really, with some assumptions, it looks like a massive enough star could actually collapse without limit. So what does that mean? Collapses without limit. It means that essentially it does what I said. You essentially remove the star from the fabric of the universe, leaving the distortion behind. And the black hole, the idea behind the black hole is, let's say you take the sun, a star the mass of the sun, and you just collapse it, and you keep on collapsing it. You get to a point when the radius of the sun is not 700,000 kilometres, which is what it is in miles, 500,000 miles. I'm going to use kilometres because
fine.
I can't remember the things in miles.
Our audience will appreciate that.
Everyone can convert it afterwards, right? So 700,000 kilometres. And you squash it down, and you squash it and squash it until its radius becomes 3 kilometres. 3. Then, there are several ways to look at this. One is that on the surface, the speed you'd have to travel to escape its gravitational pull, it's called the escape velocity, would exceed the speed of light. That's one way to think about it. So even light rays emitted from the surface, if you could squash it down that far, would just stay there. They would not escape because they'd be trying to go at the speed of light, and the escape velocity is the speed of light, and they just stop. So what happens then if a star collapses inside that number, which for the mass of the sun, 3 kilometres, is called the Schwarzschild radius, then it will collapse without limit. Nothing will stop it. And so all you will get is essentially the geometry of space and time, the curvature. And that's a black hole. So it's a thing that traps light in that sense. So you think about that. If you have this surface, and space and time are so distorted there, that if you go in across that surface, it's called the event horizon of the black hole, then you can't get out. One way to think about it is you'd have to travel faster than light to get out.
The next question is why? Or what happened before the Big Bang? So in that picture, you say, well, there was no time. So you can't ask the question. That's quite unsatisfactory. So there are people, and again, this is the future of theoretical physics in many ways, who say, well, maybe the universe has been around forever, but you've still got to explain why it looks like in our bit of the universe it was very hot and very dense, and it's been expanding and cooling ever since. So people start building theories about, well, could it have been, I mentioned I was talking to you about these brains, these sheets that we think of. Maybe two of those bumped together and separated, and that looks like a Big Bang if you're living in one of the sheets. It's speculative stuff. But there are huge problems with our picture of the universe and questions like that, brilliant questions that we don't really know the answer to. So it's going to take the next generation and the next generation. It's worth remembering that really there was no such science as cosmology, which is the talking about the origin and evolution of the universe, really before Einstein, which is 1915. So we're only talking about a science that's at most 100 years old. We didn't know about the Big Bang until the 1950s and 1960s. So really, we're talking probably just about in your parents' lifetime, or certainly your grandparents. If you talk to your grandparents, we didn't know there was a Big Bang when they were at school, but we now know there was a Big Bang, but we don't know. So we're going quite fast. But imagine what in your lifetime where we're going to get to. I mean, in 20, 30 years' time, we've had virtually double the amount of time that we've had so far to work these things out.